Hello, welcome back. For this video, we are going to talk about correlation. We will apply correlation technique to examine the relationship between interval racial variables. Correlation is a measure of association used to determine the existence and strength of the relationship between two continuous variables. 2 points here, the existence and the strength of the relationship between two continuous variables. We use correlation. When both variables are continuous, the continuous interval ratio level independent variable and the continuous interval or ratio level dependent variable. For example, your dependent variable is a test score. Your independent variable is the hours you spend for study, or your dependent variable is income. Independent variable is years of education. When both variables are continuous, the proper technique is Pearson's correlation. Pearson's correlation is a bivariate statistical analysis we use when the dependent variable and the independent variables are both continuous. So the correlation analysis asks when the independent variable increases by 1 unit, what happens to the dependent variable? Correlation is a measure of association to determine the existence and strength of the relationship between two continuous variables. For example, we use hours we study to predict the income or test scores, or we use the predictor years of education to predict income. Remember, correlation is not equals to causality. Correlation measures linear association. So a scatter plot visually preliminary displays the relationship between two continuous variables. This scatter plot can suggest whether two variables are associated. For example, the figure here shows the relationship between education and internet hours we spend per week. Our independent variable x is the horizontal axis, and the dependent variable y along the vertical axis. Each dot represents a participant. Its location lies at the intersection of years of education and internet hours per week of that participant. You may notice that individuals with lower educational attainment spend fewer hours on the internet per week, while individuals with higher educational attainment spend more time on the internet per week. Education and internet hours are positively associated. A linear relationship is one way to express the relationship between the two continuous variables. It allows us to approximate the observations displayed in a scatter plot with a straight line. In a perfect linear relationship, all the observations, all the dots here, fall along a straight line. And the line itself provides a predicted value of y, the vertical axis, for any value of x on the horizontal axis. For example, I draw a straight line on the scatter plot. Using this line, we can obtain a predicted value of the internet hours for any individual by starting with a value from the education, and then moving up to the internet hours per week axis. For example, the predicted value of internet hours per week for someone with 12 years of education is approximately 3 hours spending on the internet. Look at this example, please. Clearly, there's a very strong association between the variable, age and hours of reading. When age increases, hours of reading increases. However, at some point in the middle, when age started to decline, the reading hours started to decline. For either part, there's a positive or negative relationship in it. Here, instead of seeing a straight line, you see a tightly clustered scatter around a curve. If we calculate the correlation coefficient, you may see it's equal to 0, suggests, okay, actually there's no linear association between these two variables. That's true, but of course, it's missing the point in this case, because age and hours of reading have a relationship with each other. The bottom line is that the correlation coefficient is really only useful when we look at linear scatters. It is only useful when we look at linear scatters, not for this case. So take-home message is important to keep in mind. The correlation is only useful for measuring linear association. And second, correlation is not equal to causality. I just mentioned the correlation coefficient. It is called Pearson's R, measures the strength and direction of the linear association between two continuous variables. The direction could be positive or negative. The key property of Pearson's R include, first, R can have a value between -1 to 1, any value between this boundary. Second, R equals to 0 means there's no linear correlation between these two continuous variables. And third, -1 is also a perfect relationship. The sign minus indicate the direction. It is a perfect negative relationship between X and Y. Following the sign, so a number with a plus sign or no sign indicate a positive relationship, and a number with a minus sign indicates a negative relationship. Coefficient less than 0 signify negative relationship, while those greater than 0 signify positive relationship. When you get an R value from the software R or SPSS, R value is larger than 0 means it's a positive relationship between X and Y. If the R value is smaller than 0, it indicates a negative correlation between X and Y. So again, Pearson's R measures linear correlation. It measures the strength and direction of linear relationship, but does not apply curve linear, or nonlinear relationship I just shared. So two things need to be remembered for Pearson's R. First, the sign of the R. That indicates a type of a linear relationship, whether it's positive or negative. And second, the numerical value of the R, regardless the sign, indicate the strength of the relationship. So let's see the figure here. 1 and -1 indicate a perfect positive or negative relationship. R of 0.8 indicates a stronger relationship than an R value of 0.4. When R is equal to 0, it means no relationship between R and X and Y. Again, if R value is -0.8, it still indicates a stronger relationship than an R value of -0.4, regardless of the sign. This table is from a colleague's paper, and the Pearson's R strength rule of thumb for behavior science is listed here. And some scholars use different interpretation for the size of the correlation, but we can share some thoughts here. R value above 0.9 or smaller than -0.9 shows a very high positive or negative correlation. And R values larger than absolute value of 0.3 indicate a low correlation. So the take-home message is the absolute value of the Pearson's R tell you the strength of the linear relationship, but it does not tell whether this is statistically significant. So we need to look at both the effect size, that's the value of Pearson's R, and the p-values of the Pearson's R to tell the size. Okay, keep in mind the correlation coefficients come without units. And that's because both X and Y were standardized when we compute R. It also turned out that R is not affected by changing the center or the scale of either variable. For example, if you compute the correlation coefficient between height and weight, so it doesn't matter whether you measure weight in pounds or in kilograms. The value of R depends only on the pattern among pairs of scores. I listed the formula here, but I'm not going to go through this technical part with you. So Pearson's R is very sensitive to outlier. Outliers refer to extreme scores and require special attention because their potential radical impact on our dataset. Let us see two examples here. Left hand, red circles is an outlier. If we include the outlier, the overall correlation is 0.42. But if we remove the outlier from the data sets, the correlation is 0.009, almost a straight line. So the example tells us outlier can make a correlation deceptively weaker. And the right hand to compare, the red circle is an outlier. If we include the outlier, the correlation is 0.91. So, but if we remove the outlier, these values in the figure do not have a relationship. The correlation is almost zero. So how can we solve the problem? The take-home message is, for academic papers, for good papers, you will see they report the R value with and without any outliers. So Pearson's checklist. First, are you testing the linear association of two continuous variables? Because correlation coefficient has linear relationship between two continuous variables. And second, there should be no significant outlier. Third, these continuous variables are normally distributed. And third, if these observations are dependent of each other. If the yes to these three questions are yes, and then it's okay to use correlation coefficient. This is the end of the video for correlation. And for the last video, we will share some samples about linear regression. That's a follow-up for correlation. And you will see some paper examples.